Right, hello everyone. And this example we're going to look at how can we predict the direction of an acid-base reaction. And we have a couple of examples here that can help us predict that. So in the first one we're told equimolar quantities of acetic acid and sodium hydrogen phosphate are mixed. So that's our first situation here. And I've dropped the common ion, the spectator ion, sodium, just to make things simpler. And the way to analyze this is to look at the Ka and Kb values for the species that you are interested in. So for example, for acetic acid, Ka is equal to 1.8 times 10 to the negative 5. And for the hydrogen phosphate, it has a value of Ka equals to 3.6 multiplied to 10 to the minus 12. So meaning it will definitely not act as the base on the left-hand side. So we turn to Kb, Kb being 1.6 times 10 to the negative 7. All right, so that is our base. Our base is here on the right-hand side and on acid on the left-hand side. They then form an equilibrium on the right-hand side. So the acetic acid forms a conjugate base with, forms a conjugate base. So Kb equals to 5.6 times 10 to the negative 10 is its situation. And then the Ka of the dihydrogen phosphate is 6.2 times 10 to the negative 8. All right, and to know whether to which side the equilibrium lies, we need to compare the conjugate pairs, Kas and Kbs. All right, so meaning the Ka of the acid on the left-hand side is much larger than the Ka of the acid on the right-hand side. In a similar vein, the Kb of the base on the left-hand side is larger than the Kb of the base on the right-hand side. Therefore, this equilibrium lies to the right. Okay, meaning because the stronger species are on the left-hand side and the weaker species are on the right-hand side. Cool. Moving on, we say sodium hydroxide reacts with sodium hydrogen sulfate in a mixture, and then that forms water and the phosphate and iron. So the information that we have here is that sodium hydroxide is a strong base, very strong base. Hydrogen phosphide has a Ka of 6.2 times 10 to the negative 8. If you look it up, water is kind of neutral, so it doesn't really do anything. And there's a Kb for the phosphate equal to 2.8 times 10 to the negative 2. All right. And then going to compare, so let's put here the Kb of OH is strong, so it's a strong base. The water doesn't really have a Ka. The only Ka that you can look up is its Kw, so that's 1.0 times 10 to the negative 14. So again, if we go and compare and say the Kb and compare that with the Kb of the conjugate, we see that, well, the sodium hydroxide has the stronger Kb. In the same fashion, the Ka of the hydrogen phosphate is much stronger than that of the water. So in other words, our equilibrium here lies to the right. So equilibrium lies right. All right, because the stronger species react to form the weaker species in this case. All right, in the next example, they're told hydrochloric acid and sodium hypochlorite are mixed. Now, hydrochloric acid has a Ka, which is also just says very strong acid. So, very strong acid. The Kb, in fact, it says its Ka is very large. OCl has a Kb of 2.9 times 10 to the negative 7. Water, like we said, has a Ka of 1.0 times 10 to the negative 14 when pressed. And, or actually it can switch because it doesn't matter, Ka or Kb. And then the HOCl has a Ka of 3.5 times 10 to the negative 8. All right, so comparing here species that are still available, the Ka here and the Ka of the acid that forms, the conjugate acid that forms, we notice that hydrochloric acid's Ka is much larger. If we look at the Kb's, the Kb of the hypochlorite is much larger than that of the water. So hence, the left-hand side is the stronger situation, and it will drive the equilibrium to the right. Okay. Last situation that we will look at is ammonia. So ammonia is a Kb of 1.5 times 10 to the negative 5. And then this dihydrogen phosphate has a Ka equals to 6.2 times 10 to the negative 8. Ammonia, its ammonium, has a Ka value of 5.6 times 10 to the negative 10. And hydrogen phosphate has a Kb value of 1.6 times 10 to the negative 7. So this one is a nice easy one to do the comparison. So looking at the Kb's, we notice that ammonia has the smaller or the larger Kb. So yeah, and then same goes for the Kas. If we highlight those, we notice that dihydrogen phosphate has the higher Ka value. So that means the left-hand side has the stronger situation going to the weaker situation and the reactants. And hence again, we have a forward reaction favored. And the equilibrium lies to the right. Okay, it's almost product forming. So that is it for this question. And how you need to analyze it. Always look at Ka and Kb and at the Ka and Kb of the conjugate acid-base pair that formed. All right. Thank you for watching. I'll see you in the next video.